Okay, again, we want to give you some idea of vectors and vector spaces, because the next chapter is on vector spaces. And if you don't know much about vectors, it's going to be hard to understand vector spaces. And unfortunately, the curriculum is such that people can get to this course having had pre-calculus and calculus and still don't know much about vectors. Correct me if I'm wrong, but it used to be that your engineering curriculum would have a statics course at this point. And I believe that's no longer the case. And you haven't done statics or dynamics, all of which are based heavily on vectors. So this might be kind of your introduction to vectors. A vector in, first of all, vector in two-dimensional space can be conceived as an arrow. And this arrow is thought of as moving you from one point to another. Okay, so first idea, the vector is an arrow that moves a point in space. I'll say in a space. So I'm already talking about spaces. Right now, when you think of a space, you can think of R2, two-dimensional space, which is, of course, a plane. You don't necessarily think of that as a space, but in mathematics, yeah, that's a space. It's a two-dimensional space. Or R3, which is three-dimensional space. You got three coordinates, an X, a Y, and a Z. And that's the space we live in. But of course, anything you do with vectors in R2 and R3 could go to R4, which we can't visualize. But as you'll see shortly, we can still do vectors in R4. We can do all kinds. We can do calculus in R4. We do everything. Well, not everything. We do a whole lot of stuff in R4 or R5 or R78 or R5092. Okay? It's just a matter of we have more coordinates to deal with. So I'll be specific about that in a few minutes. Okay, so a vector right now, first idea, vector is an arrow that moves a point in a space. We'll generalize the whole idea of points and spaces later too. Everything generalizes in very profound ways. Okay, get this idea. Now, what does this mean? Well, if a vector applies to this point, if this vector applies to this point, then the same vector could apply to this point. It's the same arrow, so we can take that arrow and move it down here. Okay? This is the same vector. Same vector here as it is here. And I want a different statement. I'll say both, use a lowercase m here, both move whatever point the same distance in the same direction. Okay, if I've drawn them right, this one seems to be a little at a different angle than this one. That's because I'm looking from this angle and I'm not that great at compensating. Okay, assuming they have the same length and direction, they'll move every point, whatever point they want to move, in the same direction for the same distance. Okay, so for example, this vector might move point 6 units in a direction at, that looks like 27 degrees to me. 27 degrees relative to the positive x direction. Oh boy, no, not there. Okay, positive x direction with the direction measured counterclockwise. Okay, now let's see. Zoom is going to wipe out that much of the picture, but I think you'll be able to read that. Okay, well, there's an example. Okay, vector moves 0.6 units, whatever point, at 27 degrees relative to the x direction, meaning here's the x direction, and there's a 27-degree angle from the x direction up to the vector. So that we could say that's 27 degrees, and the vector has length 6. And this vector would also have length 6. And again, you'd have a 27-degree angle. Wherever the vector is, that's what it does. Okay, well, another way to specify a vector, this equivalent, well, I don't remember whether I had these boards cut in half last time, but it's kind of a neat, I think I did. Kind of a neat way to keep what I'm writing on this side of the board. Okay. Okay, another way, well, this vector and let's try to use as much of the board as possible. Let's just take this picture now. We've got a length of 6, and we've got 27 degrees here. Might have drawn that a little bigger, but okay. I can make a right triangle. So I come down here to the positive x direction, make a right triangle. So the right triangle then has legs along here and here. Okay. And I'm using arrows because if I start here and move along this leg and then move upward along this leg, I do the same thing to the point. The point that I start with ends at the same location. Obviously, if I do this and this, is if I do this. Okay, so this leg is going to be 6 times the cosine of 27 degrees. And it's positive because it's in the positive x direction. And this leg is going to be plus 6 times the sine of 27 degrees. Okay, so I can designate that vector now by a column matrix. So let's call this vector V. So V moves the point 6 cosine 20 degrees in the x direction. And 6 sine of 27 degrees in the y direction. We designate this by V equals 6 cosine 27 degrees, 6 sine 27 degrees, two-dimensional column vector, a 2x1 column vector. We can also say, if I is the vector 1, 0, J is the vector 0, 1, then V equals 6 cosine 27 degrees times I plus 6 sine 27 degrees times the J vector. Okay. Because obviously, if I multiply 6 cosine 27 degrees by this vector, I get a 6 cosine 27 degrees here, 0 here. Over here, this is going to give me 0, 6 sine 27 degrees. So when I add these two, I get this. Okay, now these I and J vectors can be visualized in space. Well, okay, here's the vector V. Just a little bigger than I did before. And here's the vector, not down below where you can see, but it's 6 cosine 27 degrees times I and 6 sine 27 degrees times J. Now, I'll also digress for just a second to tell you, if it's not obvious to you, the trigonometry here, then you really need to find time sooner rather than later to review basic right angle trigonometry, which you don't need the law of sines and law of cosines and stuff like that to do what we're doing here, but you absolutely need your right angle trig, okay? So if this isn't totally obvious to you, please review it. For the sake of this course, where we don't use a whole lot of trigonometry, just, as I said, basic right angle trigonometry, but also for the sake of your upcoming engineering courses, your statics and dynamics courses, if you take those are going to be trigonometry intensive, and you really need it. And for differential equations next year, you're going to need your analytic trigonometry. You're going to need a lot of trigonometry. Okay. You're going to need it in multivariable calculus too. That's vector calculus. Okay, that should tell you something. The name of the course, it's vector calculus, also called multivariable calculus. It's calculus of vectors in three-dimensional space, basically. Okay. Now, another thing, and I don't know why I want to move that board, but I guess I'll move it over just a little bit so we can use this space here. We can add two vectors. Okay, we essentially did that here. So I can say that we can designate V by this arrow, and we can also say that just graphically V equals this vector plus this vector. And looks to me like you can't see anything I just wrote. So be sure to scream if I do this. Okay. So this vector is this vector plus this vector because of this picture. Well, it should be obvious from that picture that what I've done to add these two vectors is I put them head to tail. So that this plus this equals what I get that's supposed to be a straight line. Okay. We add vectors head to tail. If I have two vectors, okay, if I have a vector if W equals this, then here's how I add them. Here's V. Here's W. And the vector that cuts across this whole path that goes from the starting initial point, call this the initial point, call this the terminal point. Here's V plus W. Okay, well, let's look at this V plus W thing a little closer. Now, I'm a little short on board space today for a reason I won't go into, if they have to do with some mistakes I made. So I'm going to pause the video for a second. Okay, so taking this idea of adding vectors head to tail, Again, we've got V, we've got W, we've got V plus W. Now, V, and I've kind of changed the direction of my vector V from over here, but let's just say that's V and this is W. Okay. Here's, why am I having trouble with straight lines? Okay. I swear it's a weird piece of chalk, or I don't know, maybe it's a wax left. Okay, here's V. Now, I'll call these vectors V sub x and V sub y. And there's some angle here, and V sub x would be the magnitude, you know, how long V is times sine theta, cosine theta, and this would be how long times the sine theta, and all that stuff. But those details aside, whatever the vector is, side direction, we call those components V sub x and V sub y. Then we got the W vector. Okay, our W vector, I can draw it in several different directions by this time. Well, we have a Vx and a Vy for W. And the Vx will be in this direction and the Vy will be in this direction. Now, you got to be careful. Vx and Vy have to take you from this point to this point. Okay, so Vx has to be in this direction and Vy has to be in this direction. Okay, and these could be vectors or they could be just numbers. Right now, I'll call them vectors. So here's a picture of V plus W. And it's not Vx, Wx, because that's a W vector. And really, I wanted to use a different color here. So now my sum of V and W is going to be Vx plus Vy and it turns out my label for Vx is in my way. I'm going to have to change that. And then I've got my Wx and my Wy. So I start here, and V moves me here and then here. So this is where V takes me from here to here. This is equivalent to this vector. And then from this point, W takes me here and then here, which is equivalent to just going directly from here to here. And here's my result. So it's as though I have my V vector here, which is equivalent to these two, and then my W vector here. Now I wrote that lightly, you might not be able to read it, but that's what I'm doing. Okay. You can see, if you think about it, that this is totally equivalent to doing it doesn't matter in which order we do these. Okay, the order of vector addition is commutative. Well, vector addition is commutative. The order in which I add two vectors doesn't matter. It's also associative. So equivalently, we have Vx and then we have Wx, which is actually on top of the Vx vector. And then we have Vy, and Wy. Wx is here, Wy is here. And that leads us to the same conclusion. The vector that we get at the end of the process is here. Same as here. If these vectors are really sketched the same. And again, I've got my Vx label in the worst possible place. So I'll say Vx here. And here we get our V plus W. And it should be clear that if I do it like this, we get the same thing. It's still not a particularly neat picture. Here, things have gone back and the vectors are crossing each other, and here they're on top of each other. So I want to do this a third time, just to emphasize. Okay, so I'm going to try to do this in a way that is a little neater. So I'm going to have Vx here, and then I'm going to do Wy. And then I'm going to do Wx. And that's absolutely the wrong place to label it. The pathetic thing is I had the picture in my head and then I labeled it wrong, but there we got it. Okay, there's Wx. And then here's Vy. And again, we've moved from this point to this point. And again, V plus W vectors are the same no matter how we do it. Well, from this, we conclude and I'm not going to prove the conclusion. I'm going to assert it. You can think about why it's true because you always want to do that. Okay, our conclusion is that from this picture, we see that the x component of v plus w is the x component of v plus the x component of w. And also that the y component of v plus w is the y component of v plus the y component of w. That's a column vector. And it's no coincidence that that's equal to the column vector vx plus vy added to the column vector wx plus wy. So that addition of vectors in the plane corresponds exactly to addition of 2x1 matrices, column matrices. So addition of vectors in the plane corresponds exactly to addition of 2x1 column matrices. And we can also call these column matrices column vectors. Okay, so I guess I've got room to write that. Okay, I think I've got a clean board here. And I think I can watch this and we'll pause the video for a second. Now I can extend what I did to 3 dimensions. Very simple. Let v equal vx, vy, vz. So now x direction, y direction, z direction. You have a displacement in the x direction, then the y direction, then the z direction. So you're going from here up to here. Nothing to it. Now the trigonometry of it is just slightly more complicated because you kind of need, if you want to deal with the angles, and sometimes you do, often you do, you need 3 angles to specify one of these. Okay. The angle of the vector with the x-axis, the angle with the y-axis, the angle with the v-axis, those are called direction cosines. Actually, the cosines of those, cosines of those angles are called your direction cosines. That's something you don't have to worry about in this course. You'll have plenty of time to worry about it in multivariable calculus. It's not that worrisome. It's not a particularly difficult concept if you've reviewed your trigonometry. Okay, so we have this. And So just say let V be this. Okay. So we could kind of visualize this in 3 dimensions. So here's X, here's Y, here's Z. So V might be a vector that starts at this point and moves you in the X direction, then the Y direction, then the Z direction. And here's Vx, Vy, Vz. And of course, then here is your vector V. And now you can kind of visualize what the vector V does. Comes forward, goes over this way, goes up. So it's kind of come in this direction. We could say okay, for Vx, Vy, and Vz no longer have arrows over the top of them. So Vx, Vy, and Vz are the magnitudes of the vectors. Okay, so that Vx let me write it out. So it leaves all ambiguity aside. I'll say it's the magnitude of Vx if in the positive direction. Or negative magnitude of Vx if in the negative direction. So that Vx is the magnitude of Vx if in the positive direction, meaning positive X direction, negative magnitude of Vx if in the negative direction, and also and Vx is a vector. This is a number. This is a scalar. This is a vector. Magnitude of Vx is the length of Vx. So the magnitude of a vector Right now, we're going to think of it as its length. And we're going to expand the idea of magnitude. Okay, I believe in chapter 5 with inner products and so forth. But right now, we can consider it to be the length. Actually, in chapter 4, because functions can be regarded as vectors in an infinite dimensional space, which is kind of a neat idea, and it's not a difficult one to understand. So we'll get to that. Okay, but it's a little ways down the road. Okay, Vx, magnitude of Vx is the length of Vx. So there's what we mean by Vx in this context. Okay, well then, and of course, Vy and Vz are similarly defined. I'm just doing Vx. Then if we have a W vector, that's a Wy. And a Wx, Wy parallel to the y-axis, Wx here. And a Wz, and of course, we have the W vector. And again, I've labeled these in a bad place, but then the V plus W, actually I might get away with this. And here is the vector V plus W in take or whatever that is. And I probably should have labeled V down here and W here. So it's clear which vector switch, but you get the idea. 3 dimensions, we just do what we did in 2 dimensions, but now we do it in space instead of on the plane. And everything follows just the same. Okay, so that V plus W is just this. Okay, meaning that if you broke W into its X and Y components, you'd have an X component in now a little bit in this direction, a big Y component in this direction, and a pretty good sized Z component in this direction. I could attempt to draw that, but it's going to make the figure too complicated, so I'm not going to do it. But you can imagine if I put this Vx and this Wx together, that Vx may be a little bigger than Vx, and you maybe have just a little bit of component in the negative X direction. Okay, the Y components go together. So I have Y component that goes over here, and then your Z components add up to something like this, and you go up that high, and you end up displacing your point from here to here again. Okay. So geometrically, this all makes sense. A little harder to visualize in 3 dimensions than 2, but it's totally analogous. Okay. Now, in higher dimensions, so I'm going to just extend this to higher dimensions. Oh, yeah. Okay. something else I need here, and I'm glad I have the space. It wasn't intentional. I ended up with this space, but I lucked out this time. Ouch. Ooh. Crude furniture in here and just got a splinter under my fingernail. I think I got it out. Didn't go far, so I'm not screaming. We could also, we got the V equals Vxi plus Vyj plus Vzk. Okay. So that we could also write V plus W equals Vxy plus Vyj plus Vzk plus Wxi plus Wyj plus Wzk. And because the order of addition of vectors, which we haven't proven, the order of addition of vectors is associative and commutative. So by the associative and commutative laws, and I hope you understand what I'm saying because it's going to be really important next week, I can rearrange these things, okay? And I can rearrange them so that I've got Vxi plus Vyj plus, it's not Vx plus Vy, it's Vx plus Wxi. I could rearrange it that way, of course, but that's not what I wanted to do. Vxi plus Wxi plus Vyj plus Wyj plus Vzk plus Wzk equals Vx plus Wxi. Okay, because we'll see it later, but this is multiplication of a vector by a scalar number. This is a multiplication of a vector by a scalar number. You have a distributive property of multiplication of scalars by vectors, so that Vxi plus Wxi does equal quantity Vx plus Wxi. It looks obvious that you ought to be able to write it down this way because that's exactly the way algebra of real numbers works. You have to establish that it works for vectors. It takes a little proof, but because of what I've shown you, the way these things add, it's pretty obvious that that's got to work. It's totally consistent with what I just said, that you can take the y component here and the y component here and add them up to get the y component of this vector. Same with the z components, this and this, give me the z component of this vector, and same with the x components. So this is just stating what seems to be obvious. Still needs to be proved, and we have to deal with some proofs. Okay, anyhow, you have this. So that because we've established associative, commutative, and distributive laws for vectors, we can write this, and that justifies this. Okay, now I say that because now we want to see how we do this in 4 dimensions. We no longer talk about an x, y, and z axis. The reason is because once we go to 4 dimensions, there's nothing to stop us from going to 40 dimensions or 400 dimensions. We don't have enough letters to label the 400 axes, the 400 independent directions in a 400 dimensional space. it's still easy to talk about a 400-dimensional space and the properties of a 400-dimensional space because they're identical to the properties of a 3-dimensional space or a 2-dimensional space. So in 4 dimensions, instead of the I, J, and K vectors, use E1. Now in 4 dimensions, we have to have 4 components. So just like I is the 1, 0 vector in 2 dimensions, or in 3 dimensions, it's 1, 0, 0. In 4 dimensions, it's 1, 0, 0, 0. Okay, then typical vector. Would be V equals, instead of Vx, we're going to number it with just the number. Okay, it's V1, E1. Be this. And of course, V1, E1 is just V1, 0, 0, 0. V2, E2, V2 times 0, 1, 0, 0, just by, scalar multiplication by a matrix. And then V3, E3, V3 times this is going to give me an V3 here. And similarly for V4. And now we're just into matrix addition, but it totally corresponds to what happens in 4-dimensional space. So this is the column vector representation of this vector. Okay, well, what if we're in 5-dimensional space? But we're going to have an E1, an E2, E3, E4, and E5. And E1 is then going to have to be 1, 0, 0, 0, another 0. E2 is going to be 0, 1, 0, 0, another 0. Each one of these is going to have an extra 0 on the end. And then E5 is going to have 4 zeros and then a 1. Okay, what if we want E400? Now, nobody in their right mind wants to write that out, but you're going to have E1 is going to be 1 followed by 399 zeros. E2 is going to be 0, 1 followed by 398 zeros, and all the way down to E400, which is 399 zeros and a 1. All the rest of it is just the way it is here. Okay. Now, the other thing is the Pythagorean theorem works in any dimension. Okay. So I'm just going to write this down. And because of time, I'm not going to go through it all. Actually, for 2 dimensions, I'm going to do it. Okay, so we have okay. Remember, we started talking about the length of V and the angle of V. Well, length of V or magnitude of V, because absolute value signs look a lot like magnitude. And when we generalize vector spaces beyond Euclidean spaces, R2, R3, R4, R400, okay? When we generalize it into function spaces and other kinds of spaces, which is where some of the most profound applications of linear algebra occur, but the linear algebra still looks the same. The meaning is just a little different. And we can't talk about the length of a function. We talk about the magnitude of a function. And the magnitude might just be the integral of the function from 0 to 1. Okay? It corresponds exactly to the Pythagorean theorem. Now, you don't have to even think about those connections yet, but when we make them, they're going to be fairly easy. We're going to be able to prove that those generalizations have the same properties as the intuitive generalization or the intuitive ideas that we get in R2 and R3, and then extend just by adding coordinates to R whatever, R400, okay? So in that case, we call it a magnitude because again, it's not really a length, is it? Okay, so length of V or magnitude of V. And by the Pythagorean theorem, that's just the square root of Vx squared plus Vy squared, because I and j are perpendicular or orthogonal. And orthogonal is the term again that we use when we get out of Euclidean spaces, R2, R3, Rn, whatever, okay? We call them orthogonal. So two vectors or two functions can be orthogonal if the, say, integral of their product from 0 to 1 is 0. We could define orthogonality that way and prove that it has all the properties of perpendicularity. But it isn't perpendicular anymore because functions don't exist in real space. They exist in, vector one dimension, one variable, has a two-dimensional graph. So anyhow, again, we deal with that later, but these geometric interpretations get generalized all over the place, which is why you got to understand them. The linear algebra of it is pretty much the same. Now, some function spaces are typically infinite dimensional, so you got to deal with that a little bit. We don't go too deep into it. Okay. So because these are perpendicular, I and j, these vectors make a 90-degree angle, so we have a right triangle, and we apply the Pythagorean theorem, and there it is. Okay? I'll skip 3 dimensions. In 4 dimensions, just write down the same thing, except you got 4 of them to square. It's easy to prove in 3 dimensions but that makes perfect sense. Okay. And I'm not going to take the time to do it, but it's very easy to prove and illustrate in a way that'll convince you. So take my word for it. You might see that in your text, but I'm not sure you do. But you're certainly going to see it in multivariable calculus. So yeah, right now, just accept it, that it makes perfect sense. It's totally consistent. Everything works. Okay, well, there we've got some pretty good stuff. Now I want to go on, figure out what board to use here. So let me pause for a second. Okay, so there's a little bit of the flavor of this thing. Again, review trigonometry, at least right angle trigonometry. Make sure you're up on that because otherwise you're going to have trouble understanding some things next week. Doesn't go much beyond what I've done. Yeah. If you know the x and y components of a vector in R2, then the magnitude of the vector is just what I said by the Pythagorean theorem. So right there you have one important connection. The angle of the vector, in case you need it in R2, is the arctangent of the y divided by the x component. And then if the x component is negative, you got to add 180 degrees. That's just standard high school trigonometry. And it should have been covered thoroughly in your second semester pre-calculus course. And we find that that's not always the case in pre-calculus courses that come from elsewhere. But the course, at least that we teach on campus, really does that. And I think most of the dual enrollment courses do a good job on the right angle trig. All of them, as far as I know. So the courses you get through us do pretty well with the right angle trig. Not all courses get to the vectors, and I'm not sure that the system, even VCS, even requires a whole lot of vectors in second semester pre-calculus, so it's like nobody knows it. Okay. So what's this leave us with? We've seen some basic things here. One, vector addition is associative and commutative. So we can rearrange any sum of vectors any way we want. We can group them any way we want. We can move them around using the associative and commutative laws. Okay, so we applied that down here. Okay, we did this. Oh boy, what a word in front of this. Multiplication. Of vectors by scalars. And by a scalar, well, your example of a scalar here is whatever you're multiplying by the vector, a number that you multiply by a vector. Your scalars might not even be numbers in more generalized spaces. So we say scalars, not numbers. Okay, they're members of the field. You have a scalar field and so forth. You don't need to know what a field is. That's a little later in an abstract algebra, or at least a baby abstract algebra course. That's something you might not even have in your future, probably don't. So multiplication of vectors by scalars. It's distributive, which is why I could write Vxi plus Wxi as a quantity Vx plus Wx times I, because this multiplication is distributive, okay? And similarly, there are actually two distributive laws, okay? If I multiply a number by a sum of two vectors, okay, I can express that by saying, well, of course, the sum of two vectors is a single vector. So if I multiply that number by that single vector, I get the same thing as if I multiply that number by the first vector and then multiply it by the second vector and then add the vectors that I get. Now, whether you understood that when I said it, if I wrote it out, it would be totally obvious to you. You wonder, why are we even mentioning this? Obviously, that's what you do. Well, we still have to be formal about this because these things are going to get generalized, and you're going to go places with these things that you wouldn't even suspect existed. Okay, that's how it comes out. Multiplication of vectors by scalars is distributive. Another formal property. Multiply a vector by a unit scalar. For right now, think 1. I'll say yields the original vector. In others, doesn't change. So if I multiply a vector by 1, I get the vector. If you multiply a vector by a scalar, the magnitude of the vector gets that many times bigger. So you multiply the vector by 3, the magnitude gets 3 times bigger, meaning the vector gets 3 times longer. Not going to write that one down. And I'm not going to write down every possible property. Adding a 0 vector to another. And instead of another, I'll say vector V. You get V. Okay. A 0 vector keeps the point where it is. Remember, a vector moves a point to another point. Okay. And if you take a vector that moves from here to here and add a vector that doesn't move it, you still end up here. Very simple. Okay, well, there are a number of other properties, and we'll look at them more formally when we get into chapter 4. Again, we're a little ahead of ourselves on chapter 3, but I want to get you thinking about these things. Also, give you this much introduction to vectors in 2- and 3-dimensional space and how they're very easily then extended into higher dimensional space. The only difference in higher dimensional space is you got to use subscripts for the unit vectors in the directions of your coordinate axes. And that's not difficult. Again, we use subscripts because you don't run out of numbers. If I want to do E400, that's easy to write. If I've got 400 different letters to remember, well, nobody's going to do that. Might be a few people in the world who could, but the rest of us aren't going to listen to them. Okay, well, there it is. So I'm just going to close out here, ask if you've got any questions, which I'll be glad to answer, but of course, another class coming up. Just got a couple of minutes for that.